Welcome to all the students for another lecture of engineering physics. This time I will be teaching you about the diffraction of light, and in this diffraction of light I will be talking about n-slit diffraction. Alright, so to start with this n-slit diffraction, I would like to first discuss very briefly that what is diffraction. So, as you know that if we talk about the very common definition of diffraction, so we generally say that by diffraction of light, we mean that there is a bending of light. Light is bending around some obstacle, and that is called as diffraction. So, the diffraction, it can be divided into two parts. That means theoretically we can study diffraction in two parts, in two types, like Fresnel diffraction and Fraunhofer diffraction. In the Fresnel diffraction, the distance of the screen from the aperture is finite. That means the sources and the screen, they are at finite distances, all right. Whereas in Fraunhofer diffraction, the distances of the source and the screen, they are infinite. So, we will be talking about the Fraunhofer diffraction type in this entire syllabus of engineering physics. The diffraction which we talk about is the Fraunhofer diffraction, all right. So, now we quickly talk about that what is the meaning of grating, or what we mean by n number of slits. All right, actually if we talk about the grating, it is the arrangement consisting of large number of parallel slits of the same width, and they are separated by equal opaque spaces, and this whole arrangement is known as a combination of these n number of slits, and also it is known as the diffraction grating. So, how this arrangement is made? It is made by constructing ruling equidistant parallel lines on a transparent material such as glass. It is a glass plate, plain glass plate. On that glass plate, the certain lines, parallel lines are drawn with a fine diamond point, all right. So, the ruled lines are the opaque to light, so light is not able to pass through that ruled lines, all right, while the spaces between those parallel lines, in between the in those spaces, the light can pass on. All right. So, light is actually bending at the edges of those ruled lines, and that is how light is diffracted, and that is how this grating is playing the role for the obstacle for the light, so that light can diffract. All right. So, this is how it is, this is how it looks. See, you can see here we are having a number of slits. See, this is the slit. The slit is a small opening, this part which is open. So, this is the slit, and you can see that they are arranged in a series, all right. And you can see that this is the part where the light will not be able to pass on, the opaque space, the opaque part, and the spacing is this part, all right. So, the light can pass on here, and these arrows of light can show you that how the light is bending at the edges of these slits. So, this is how it is playing the role of diffracting the light, all right. So, here this is what the bending is going on. This is how the light is bending, all right. So, this combination is known as the combination of n number of slits, and the combined name given to it is the grating. So, you can see parallel beam of lights are incident, all right, and then they are diffracted. And if we want to study these diffracted beams, so we have placed a lens, they will pass through these lens and then they will converge, and we have placed a screen, and so that the converged pattern will be obtained on the screen, and that will be the diffraction pattern due to these n number of slits here, or the diffraction pattern due to the grating. So, we will observe this pattern experimentally, all right, and also we can have a theoretical study also, that how the pattern is going to look like, where the positions of the maxima and the minima will be obtained. So, that will be the study for the diffraction of this part. All right, here you can see that this opaque area, this region is given the name as D. It is specified as D. This is the opaque part, and then this part which is open, which is the slit part, that is the width of the slit, and it is generally given the name as small e. All right, so small e is the width, slit width, and the spacing which is present between the slits, that is the D. All right, and theta is the diffraction angle. This part where the beam is diffracted, the beam is diffracted through this angle theta. So theta is known as the diffraction angle. All right. So and here we are having the expression of delta is equals to D sine theta. So what is the role of delta here? Now what happens? If we look at this single slit here, all right, so the beam is diffracted from this single slit and the beam is making a certain angle theta, all right, which is already shown here. All right, so this, if we look at only this set of beams, so this is the, this will be giving us the study of diffraction due to the single slit. All right, but here you can see there are a number of slits. So we will have to take the contribution of all these n number of slits. So what will happen if we take the contribution of this slit? So again, it will have the same type of diffraction. All right, each and every slit single in the single form, it will have the same behavior. But what happens when all the diffracted beams from these single slit, they meet somewhere, so they superpose. All right, you can see they converge. So they superpose. So when we are able to see the effect on the screen, so that is the superposed effect, the combined effect of all the n slits. So we need to understand that how the combined role is there. All right. So if we look at this second slit, all right. So what is the difference between the beams coming out from the first slit and the second slit? The difference is this part here. I am dropping a perpendicular from the first beam to the second beam, and you can see this part. This is the extra path that the beam which is coming out from the second slit is traveling. All right. So it is traveling this extra path. So this is the path difference between these two beams, this first one and the second one. Again, when we come to this beam, the third beam, again this beam is traveling this much path, extra path. Again the fourth beam and so on, and the n number of slits. So all the diffracted beams which are coming from the slits, they are traveling some extra path as compared to the first diffracted beam which is coming from the first slit. So that extra path is playing the role in superposing them. So if we want to study this diffraction pattern theoretically, so we need to calculate this extra path here. It is this path I am talking about. So we need to calculate this extra path. All right. So how do we calculate this extra path? If we see here, this angle is theta. All right. We drop a perpendicular from here. All right. So this also becomes theta. All right. This part is D itself, and here we are having E. So this delta is actually, all right, the part difference becomes, it is E plus D sine theta. All right. This is E plus D sine theta. This part is E plus D sine theta. This is the path difference which is present in the first beam and the second beam. And this part will go on changing, because this distance D will go on changing. Because right now, if we look at the diffracted beam from the first slit and the second slit, then between them the spacing is D. But when we look at the diffracted beams from the first slit and the third slit, so between them this distance does not remain D now. It becomes 2D. All right. Similarly, if we go on to the fourth slit, it becomes 3D and so on. So this distance goes on changing. All right. And this is how the path difference goes on changing from delta to 2 delta, all right, 3 delta, and so on, and n delta for the n number of slits. So if we calculate the path difference from the first slit and for the other slits, so this is how the path difference is going to vary. And all together, if we sum these path difference, so we will get the resultant path difference, and that resultant path difference will be giving the study of the diffraction pattern which is obtained due to the n slits. All right, so this explanation is given here, like here. All right, this part we have already done, that E will be the width of each slit and D will be the separation between consecutive slits, and then E plus D. All right, E plus D we have already understood that what part is known as E plus D. And to emphasize its importance, the name is given to this E plus D, that is grating element. All right. So this is the grating element. Now here it is shown in detail how we can understand the path difference which is generated due to n number of slits. Initially, what is done? Initially, the amplitude of the wave is calculated by capital R. All right. So capital R is this A, this is the amplitude, and then sine alpha by alpha. This whole thing is the amplitude for the diffracted beam which is coming out from the single slit. All right. We must not forget that each and every slit is going to diffract the beam. All right. So the behavior will be same. So this is the amplitude of the beam which is diffracted due to the single slit. And then we are having the role of the path difference, that is S1 and S2, that is slit 1 and slit 2. All right. So this is S2M. This S2M is to show the difference between the path which is traveled by the beams from S1 and beams from S2. So like we have already discussed, we have done this, E plus D sine theta is the path difference between the first two consecutive slits. All right. And then path difference, we use this path difference and substitute in the formula of phase difference, that is 2 pi by lambda, and then the path difference. So the phase difference, which is generally denoted by delta, turns out to be this part, and this is equal to 2 pi by lambda E plus D sine theta. Right. So this whole thing, it's a long expression. So to simplify for further calculation, let us say that this name 2 beta is given, the name 2 beta is given to this entire expression. All right. And then when we have the final expression of the amplitude, then we will substitute for beta like this. All right. Just now for the calculation, we have taken this. So we were discussing about the resultant amplitude at the point P. P is that point which we have obtained on the screen due to all the diffracted beams from the capital N number of slits. This capital N is for the number of slits which were arranged in series. All right. So then the common phase difference 2 beta, we have discussed already in the previous slide that this beta, this phase difference is going to vary like this. The delta part will be common, but it will have different values like delta, 2 delta, 3 delta, and so on, depending on the number of slits we are taking into contribution. So that part is mentioned here. All right. So when we write down the resultant amplitude at the point P, which was on the screen, so the resultant amplitude comes out to be capital R sine 2 n beta by 2 and then sine 2 beta by 2. And then further simplifying this, we are having capital R sine n beta by sine beta. This is the amplitude due to the n number of slits which were diffracting the beam, and then the diffracted beams were superposing. So this is that contribution where this capital R is the diffraction, is the contribution which is obtained due to the single slit diffraction. due to the slit which is showing the diffraction individually. So that is capital R, which is already shown here, this part. All right. So this will be substituted here, and the final amplitude can be written like this. This R dash is A sine alpha by alpha and sine n beta by beta. So you can see in this expression, isn't it? This part we are not having any n type of term. That means this part is showing the contribution of single slit. But if we see this term, all right, so we are having this n contribution here. So this part is showing that superposition part, that n number of diffracted beams are there and then they superpose. So this is showing the contribution of n slits. So this is a part which we must understand, that if we write down the amplitude, the resultant amplitude due to the n number of slits, so then we will be having the individual contribution of the slit also, and we will be having the combined effect of the n number of slits also. So now we have to study this part. How do we do it? In the diffraction, what is our main theoretical part, which we, with the help of which we study the entire diffraction pattern theoretically, is the intensity part. Whereas in the interference, it is the path difference part only, by which we can study the entire interference pattern theoretically. So in the diffraction, we are having the intensity part. So once we are having this amplitude, we can just square this amplitude and it will give us the intensity of the entire diffraction pattern, which is obtained due to the n number of slit, capital N number of slits. So we do this thing and we find out the square. This is not 2, it's the square. It has to be like this. So when we square, so we are having A sine alpha by alpha square and then sine n beta by beta, sine n beta and upon sine n beta whole square. So this part will be the for the intensity of the diffraction pattern, which is generated by the n number of slits or which is generated by the diffraction grating. All right. Again the same, this part again for the intensity also we will note that if we talk about the first term in the intensity, so we are having A square and then sine square alpha by alpha square, and this will give us the intensity for the diffraction pattern, which is obtained due to the single slit. All right. And because there is no term of capital N here, no contribution of number of slits, and the second part will give us the contribution of capital N number of slits. Now, one interesting thing also we can do from here, like what happens if in this expression of the intensity, what happens if we substitute n equal to 1, suppose. If we put n equal to 1, that means n is 1, that means n is the number of slit, and just now for this case we are having what? We are considering that we are having only one slit, all right, single slit. So what happens to the intensity, we can see. So what will happen to the intensity? The intensity will be how much? From the expression you can see, this will be I, and it will be this A square sine square alpha we are having by alpha square, this part, all right, and then this n equal to 1, so this becomes sine beta, and again it becomes sine beta, and this cancels off, isn't it? So I comes out to be how much? I comes out to be A square and sine square alpha by alpha square. So if you look at the diffraction pattern, all right, for the single slit, if you look at the diffraction pattern for the single slit, you will be finding the expression of intensity is just exactly the same. All right. If you go through the single slit diffraction pattern, so you will be able to find out the expression of the intensity like this only. All right. We can try it for 2 slits also, double slit. So what will happen for double slit? We just have to substitute n is equals to 2. I am discussing this just so that you can see how the intensity expression is valid for single slit also, for double slit also, and of course for n number of slits it's valid. So for n is equals to 2, what we are having double slits. All right. So double slits we are having, and we must look into it that what is the value of intensity here. So the value of intensity is how much? This part remains a square and then sine square alpha by alpha square here in the first part. What happens to the second part? We are having sine 2 beta, isn't it? N equal to 2, we are having sine 2 beta, and then we are having sine beta. All right. So this is square. So sine 2 beta, so this part is, so we can just expand sine 2 beta, isn't it? So when we expand, so this is a square, sine square and alpha square, and we will have 2 sine beta and then cos beta. We will expand this sine 2 beta, and we'll have this, and in the this part in the denominator we are having this, and this sine beta and sine beta, it cancels off. All right, and we are having square of this part. So this becomes it is like this. If you go through the if you go through the expression of the double slit diffractions and you find out the expression of intensity, so you will be getting the same expression. We will have 4 here, so 4 comes out. This 2 square is 4, so 4 comes out here, and then we are simply having this cos square beta here. All right. So this is the expression for the double slit if we talk about it. All right. So and again here what happens if we look at this expression, again this will be giving the contribution due to a single slit, whereas this cos square beta will be giving the overlapping or the superposition of the diffracted beams from the first slit and the second slit. So that is why this term cos square beta has come. So it will be showing the superposition. All right. So this is what we can study from this expression of intensity here. All right. And now what happens? Now this expression of intensity is going to give us the study of the diffraction pattern. So what do? We study this expression of intensity for different positions. Like we can study for the positions of minima, for the principal maxima, and we can study for the secondary maxima. These are the highlighting positions in a diffraction pattern. So we can use this expression of intensity and we can do that. All right. So first position which is discussed at priority, that is the position of the principal maxima. All right. So we can use this type of expression for that, I think. All right. Let us see what we will use. All right. So this part we were discussing that we will talk about the position of principal maxima. All right. Principal maxima is that position where the intensity is maximum in the entire pattern, in the entire diffraction pattern. These are the positions where the intensity is maximum. All right. So to find out these positions, we must look at the expression of intensity, and we must look at this term sine n beta by sine beta, and we must understand that when will be the intensity maximum, what will happen to the value of beta so that the intensity is maximum. So one suggestion can be there, one method can be there, that this sine beta must have the minimum value, or this sine beta must vanish. In that case, intensity will become maximum and we will be able to study the position of principal maxima. But there are some problems. If we take that value, sine beta vanishes, so then this sine n beta by sine beta, it becomes indeterminate. All right. So that will be a problem. So now we first we have to solve that problem. So when we do, how do we do it? Like we understand that what is exactly is happening. We apply the limit that beta is tending to n pi. All right. If we do it, so then what will happen to this term? we will differentiate, that is a type of rule, the L hospital rule, that we can use here. All right. So when we are having the indeterminate type of thing occurring, so then we can use that rule. So that is what is done here. We just differentiate this sine n beta by beta, and we differentiate this sine beta by this sine beta. So when we differentiate, so what will happen? This will be cos n beta, n cos n beta, and this will be only cos beta. And then we put the limits beta tending to n pi. So when we put this, so then beta tending to n pi will give us this capital N, because for cos pi we are having -1. All right. So we will get minus values cancelled out, and that n part will be there. So this whole part, after applying the limit, will come out to be capital N. All right. So this will be capital N. And now we substitute the value of this capital N in the expression of intensity here. So it becomes n square, and the intensity will be I is equals to n square times this a square sine alpha square by alpha. All right. So this will be for the intensity which the principal maximas are going to have. If we look in the experimental diffraction pattern, which we can obtain experimentally, so we will be having these values of intensity for the principal maxima. All right, and the condition is this, but the condition is slightly modified by this limit approach. All right, so beta for this principal maxima, remember that sine beta equals to 0. So we must understand that what we will get for beta, is plus minus n pi, because you remember that we have substituted something as beta. Actually, there is nothing like beta, but we have done a substitution. All right. So we have to go back to that substitution. So beta is equals to plus minus n pi. So here we will have what? Here we will have pi, and then E plus D must be here. If you recall that expression where we had beta. All right. So that was 2 pi E plus D sine theta by lambda. So we will have here pi and E plus D. This is the expression which we must have here. All right. For beta. So we are having beta is equals to plus minus n pi. So actually we are having pi E plus D sine theta by lambda is equals to plus minus n pi. All right. And we have to understand that n can take what values? So n can take values 0. All right. N can also have values 1, 2, 3 and so on. If we say that n is having a value 0, so we mean that we are talking about 0 order principal maxima. If we say that we are having n equal to 1, so we can say we are having first order principal maxima and so on. N equal to 2 will give the second order, 3 will give the third order and so on. So in this way we have identified one position successfully for the diffraction pattern. All right, that is the position of the principal maximas. Once we identify all the positions theoretically, we will be looking at the pattern which is experimentally obtained, and then we will understand what positions we are talking about. Now, after the principal maxima, the next position which we obtain in the pattern, that is the position of the minima. All right. So this will be the next position which we will identify here. Every time we identify some position, we have to take the help of intensity, because I have told you in the diffraction it is the intensity which is monitoring the entire pattern. All right. And in the interference it is the path difference. So we again go back to the expression of intensity here, and again we have a look that what will happen if intensity is minimum. All right. So we are not talking about this term because it is for the single slit. All right. So we are, every time when we say that what will happen, we mean that what will happen with this term. So for intensity to be minimum, if we look at it very carefully, this numerator sine n beta can give us the position where the intensity is minimum. because it should be minimum. All right, let us see how it will help us. So here, so this is sine n beta is equal to 0. So when sine n beta will be equal to 0, we can expect that the intensity is minimum. But the condition we have to see here, sine n beta is 0, that condition must be fulfilled. But the condition which should also be taken care of is this part. Sine n beta cannot be 0. Sine beta, it cannot be 0. Strictly, this cannot be 0. All right. If this is equals to 0, everything goes away. We are not going to get the position of minima. All right. Because we will reach here. You remember here, because sine beta was 0 here almost. So therefore, we cannot have a condition sine beta equals to 0 for the minima. It's very important to remember here that we can get a minima when sine n beta is equals to 0, but strictly sine beta does not equal to 0. All right. So when this happens, sine n beta equals to 0. So we will get n beta equals to plus minus m pi. It's not beta here. By mistake, it's written, it's pi. Plus minus m pi. All right. And like we have put a condition on sine beta not equal to 0. So we will put a condition on m also. All right. It cannot take any value randomly. No, it is having a restricted value. All right. So let us see what are the values. Like it can take values m equal to, all right, it cannot take values m equal to 0. It cannot take values 2 pi, all right, 3 pi, pi. It cannot have these values. All right. Instead of pointing out that what values m can take, here we need to take precaution that what values it cannot take. So it cannot take these values. All right. Because again the same thing, if it takes these values, so again this condition, all right, it becomes the condition, it matches with the condition of principal maxima. And all of us know that at the same position, the maxima and minima, they cannot occur. All right. So that is the part which we need to take care. So, all right, which values it cannot take. All right. And now we again, like whenever we are getting values for beta, so we go back to the diffraction angle theta, because that is exactly the measurement parameter. Beta we have defined for our convenience. So n beta is equals to plus minus m pi will take us to this expression, where capital N is as it is, but beta is pi e plus d sine theta by lambda, the same expression here for beta, and is equals to plus minus m pi, and then pi and pi will cancel off. All right. And we are left with this part, capital N e plus d sine theta equals to this plus minus m lambda. All right. So this is the condition for minima in the diffraction pattern due to the single slit. This is the condition for minima. All right. So again, the second position we have identified now. All right. Capital N is the number of slits. All right. The third position now, this part, the third position. The third position is the secondary maxima. All right. It is the intensity lies between the minima and the principal maxima. That is what can be understood what is the meaning of the term secondary maxima. It is the position where the intensity is lesser than the principal maxima, but still it is larger than the minima. All right. So what is the position of the secondary maxima in the case of this n-slit diffraction? There are n minus 1 minima between two adjacent principal maximas. There must be n minus 2 other maxima between two principal maximas. All right. So it is said about the secondary maxima. Why they are telling about minima? From here they are telling, because we have imposed a condition that for minima these values cannot occur. all right. So they can, when we impose the condition, it means that this M can be having these values, M can have these values. So that is why they are saying, that the minimas will, if there are n number of slits, so there will be n principal maximas, but there will be n minus 1 minimas, all right, and then there will be n minus 2 secondary maximas. That means 2 secondary maximas between the principal maximas, all right. Suppose 0 order principal maxima we have and the first order. So in between we will have 2 secondary maxima. That is what is meant with by this definition. So now we need to understand how we can calculate this secondary maximas. All right. For the, if we look at the intensity expression again. All right. So we have imposed a condition that at one situation the sin n beta will be minimum. The other situation sin beta will be minimum. So both the conditions have been used now. So how do we calculate this secondary maxima? So we have selected a different option or a different way to find out the secondary maxima, and the best way is that if intensity is having maxima or minima, so the differentiation would turn out to be 0. All right. So the differentiation would turn out to be 0. This part we have used. All right. So we differentiate this intensity expression like this. All right. When we differentiate, so this is alpha, it will not be affected by beta differentiation. And the next part is sin n beta by sin beta square. So this whole part will be differentiated. All right. And now this entire expression di by d beta will be equal to 0. But what happens? This cannot be 0. This part, this is alpha, all right. So it is useless saying that it can be 0 because it has nothing to do with that differentiation. So this part even cannot be 0 because we had looked at the previous situation that it becomes indeterminate, and so those problems. So for this expression, only this is the expression which can go to 0. All right. So in this n cos n beta, sin n beta and minus sin n beta cos beta upon sin square beta, this will go to 0. And in this numerator part will be equal to 0, like n cos n beta sin beta minus sin n beta cos beta, this is 0. And then we substitute and then we obtain this term in terms of tan. So n tan beta is equals to tan n beta. So it is this value of beta which is coming from this expression which will give us the position of secondary maxima. But it is complicated. So how do we calculate? So we go to the to take the help of this right angle triangle, and as we have obtained this condition, with the help of this condition we draw this triangle. All right. So here we are having this n beta angle, and here we are having this hypotenuse as n square plus cot square beta whole square root, and then this cot beta is the base, and then this perpendicular is capital N. With the help of this triangle, we can now find out the value of sin n beta, because sin n beta we are having in the intensity, that's why we need this value. So when we find out, we are having this n upon n square cot square beta and square root. So we substitute these values in the expression of the intensity. You are familiar with this expression, sin square n beta by sin square beta. And when we substitute, we are having this part of the value. All right. And we put the value of cot beta now here, that is cos square beta by sin square beta. So that cancels off. This sin square beta will cancel off. And here we will have cos square beta. For cos square beta, we can write down this 1 minus sin square beta. All right. And then this value we will have n square sin square beta plus this cos square. All right. We further can simplify. This becomes n square upon 1 plus n square minus 1 sin square beta. All right. So when we put this value of the expression in the intensity, so we are getting I, and here we were having what? Here we were having this a square. So that a square in terms of intensity will become I naught. and this is sine alpha by alpha square, all right, and this part is coming from sine square n beta by sine square beta. So, this expression we are getting for the intensity. Now, how do we study this expression? That means intensity of secondary maxima upon intensity of principal maxima. So, if we do this, so intensity of principal maxima is how much? This part. So, it goes off the n square part also. So, it goes off, cancels off. So, we are left with simply what? 1 upon 1 plus n square minus 1 sine square beta. So, this is the ratio of the intensity of secondary maxima upon the intensity of principal maxima. Alright. So, this study we can do for the secondary maxima. Alright. And here is at last the pattern, diffraction pattern as it is obtained experimentally. You can see this is the largest peak. So, this is the 0 order principal maxima, alright. And then here we are getting the first order, second order, third order. So, these are the principal maximas, alright. And in between the positions of minima, this part, and these are the secondary maximas which are shown here. These are the secondary maximas which are present here in between the principal maximas. So, this is how this intensity pattern it occurs or it appears when we see it experimentally, all right. And in this way we can first find out these positions, various positions in this diffraction pattern, principal maxima, minima and secondary maxima, and then we can identify these positions in the experimental pattern which is obtained, all right. And that was all for the n-slit diffraction, all right. We can further talk about some other regions in this n-slit diffraction, but we will do that in the other lecture because those are known as the absent orders or the missing orders. So, for that we are having another lecture, all right. For today, so much of discussion is sufficient, all right. For the reference, you can refer to these books which we are generally using in the BTech first semester for physics, all right. Thank you.